Welcome. I'd like to show you a little Blink assembler program and how you can make that. Basically, to start out, you go up here to Project, you go to New Code Composer Studio Project, you type, I put in Blink assembler in here. You need to make sure you've got the right processor over here in this box. You can filter for it using this box. And then you want to check empty assembly only project. And when you do that, if you had a name in here, you could click finish and it would finish and create the project for you. I also renamed the main.asm file by right-clicking on this and hitting the rename button. And so I've actually created this program before. Let's look and see if we can understand what's in here. When you come up with it, everything except the stuff in this main loop is actually created for you. But this is the code I wrote from 26 through 38 here. That's basically what I created. But let's look at what was created for us. First of all, it has .c declares, and it says mfp430.h. It defines reset, and this is so that the linker will know where to start. And .text, that means underneath here is where all the assembler program is. And we have a .retain, which overrides the conditional linking and retain the current section. Then we retain refs to contain references, to retain any sections that have references to the current section. And then down here, here's the reset vector. That's actually where it's going to start. And remember up here, we defined that. This is where it's going to start. So first thing it does is it moves immediate __ stack end to the stack pointer. Now, stack end is actually a global variable that was defined somewhere else, and it basically refers to the section that's the stack section, and that follows the stack end, and it really it points to the highest RAM location. And then we have this label stop watchdog timer. We move .w, these two things here into the watchdog control register, which essentially stops the watchdog timer. That's similar to what we had showed you in C before. And then there's this main loop here, and this right after the main loop here is the stuff that I put in. This program is to blink the LED on the MSP4305529 Launchpad, and we could put a little note here. The LED is connected to port P1.1. In other words, port 1, pin 1. And so if you see what we do here, first of all, we set immediate 1. In other words, we put a bit set the first bit of the address of P1 dir. So P1 dir is a data direction register for port 1, and that says I want pin 1 of P1 dir to be a high, making that an output. That's the direction will be output for this port. That's what I need for an LED. I'm trying to put out a signal to make the LED turn on and off. Then I have this label here, outer, and I XOR .b. The reason it's a .b is because P port 1 is an 8-bit port, and that's why this was a .b on this bit set up here. So I set bit 1 and the address of P1 out, which is actually the register that you write to actually change the output of port 1. And then I move a big number. This is 0x2710 was determined experimentally to be a nice delay. And then I have an inner loop label, and I decrement this R5 that I just loaded with the big number. and then I test to see whether it's 0. If it's not 0, I jump not equal back up to inner, and I decrement it again and test again and keep going through this loop, burning up time until that thing gets down to 0. When it gets down to 0, you hit this jump outer thing here, and it'll jump back over here. This no-op is a no operation, and it's actually the assembler warned me that I needed a no-op after a jump. And so I just put it in there to get rid of the warning. I think that's one of the fine print things when you look in the assembler manual for the MSP 430. Down here we said before there's the global stack end. This is the section stack where the stack is, and it starts with stack end, and that's made into a global variable so anybody can grab it. And then we have the section reset, and it has a label here, reset, and that is where we actually start executing. So those help. These are the interrupt vectors. This is the reset interrupt. When you push the reset on the board, it'll start executing the code at label reset, which is right up there. And so that's the program. I think what we'd like to do is assemble it here. So let's click the little build button, and it looks like it finished just fine. Now I'm going to click the debug button, and we'll start debugging this thing. And so here we are. I'd really like a better perspective on this, because I don't care about the variables so much and the expressions, but I want to see the registers, and I'd really like to see them in a long thing going all the way down. And the other thing that's really important to me is the assembler that we're actually created. I'd like to kind of see that as I step along. And I really don't need to see all this data right here. And the console, it said the loading is complete, and we're using this much RAM and so on. And that's all nice, but I don't really care so much about that. So I'm going to go into this other perspective, which I created by just dragging these things around. It takes a little doing, but it's not too hard. So here's the perspective that I'd like to look at to see what I want to see. You can go over here and read the core registers. You can see that they're core registers. You can see what values they have. Notice the PC is pointing at 4400. That's not surprising, as that's usually the start of the flash memory. The stack pointer is also 4400, which is the highest address in RAM as well, I think. But things will get rearranged when we actually run the program. So those are the core registers. We're familiar with those already from before, I believe. But here we have the port 1 and port 2 registers. And notice that these are 2 nibbles, so that's 1 byte of information for each one of these things. This is where we would read input if we were using the port for that, and we could actually click this and see that that's what we're seeing for input. Port 1 output, this is where we write to this, and right now there's a 1 on port 1 out. And this one's the data direction register at 0, so nothing's an output. And then this guy right here is a resistor enable register, and we'll talk about that. It enables pull-up resistors, and that's especially useful if you're looking at port 1 as an input. And you can look at the bits of those as well if you want. And then there's this drive strength register, which allows you to put out more current if you need to. And the port 1 select register, which allows you to select there's optional things that the port 1 can do beyond input and output. And so you can look at that. And then there's also port 1 interrupt vector. You can actually generate interrupts by hooking voltages to port 1, and it will generate an interrupt if you set it up right to execute an interrupt subroutine. But we're not going to do anything fancy like that. We're just going to run this program over here. And I think, rather than run it, I could run it and I'd see the little light blinking here, but I don't really care to do that. What I'd like to step through it and show you what's going on. So let's look at the core registers here first, because the first thing we're going to do is initialize this stack pointer, so this is going to change right here. So here we go. Okay, there, the program counter moved down to 4404, and you know, it would be nice if we could see that, but I guess it doesn't show. It just shows where we are here. If I actually looked at the disassembler window, which I could do right here, disassembly, you could actually see 4404, there it is. And here's my assembler that I created, but you can now see the addresses that I like. Maybe that's even better than this. So I'm going to get rid of this guy, or just get rid of this guy right here. And I'm going to scoot this guy over. This is probably even better perspective here than what I've got before. So we're looking at the core registers over here and the disassembly right here. So we just set the move the first one down, and the next thing we're going to do is that should have also set the stack pointer, I think. Let's see where we are. I click this little guy right here. Okay, 44A. So the stack pointer was set at 4400. Must have been that before. And now we're looking at, you can see the assembler code, by the way, right here. You know, it was showing the C code, but now it's just showing the assembler code. And so I should have set the port 1 direction register, or actually I'm going to do that this next time. So let me close the core registers. Let's look at the port 1 direction register right here. P1 dir, right now it's 0, but you can see it should be this P1 right here. So let's move this value over a little bit so we can see just a little bit better. So let's step, and it should change that P1 dir 1 from a 0 to a 1. Oops, it did P1 dir 0. Okay, so is that what I actually wanted? Notice it calls it address of port A, PA out here, and here I had address of port 1. That turns out that PA is port 1 and port 2 put together to make a 16-bit port. And the disassembler doesn't recognize the difference between them. It's the same number. If you hover over this guy, it's port A, it's 0x002. And if I hover over this guy, maybe it's not gonna tell me what it is, but it is the same thing. So right now I can look at the board and tell you that the light is off at this point, but let's see what happens when I click it on. Okay, it just turned on, and that's because, remember, P1 out had a 1 in that position down here. Now it has a 1 right there, and P1 out, that's what just got changed. And so let's keep clicking through. Now I decrement, and test, jump decrement, and this is going to take forever. So now I'm going to click this guy over here, and it should start blinking, and yeah, it's blinking quite quickly. So hopefully that was useful, that you could see how to debug things in the assembler, and how you can look at the register values and so on. So that's good for this video. We'll stop it here.